All right, so we're going to finish up section 5.4. Okay, what we left off with yesterday was kind of getting away from the idea of drawing vectors and starting to look at a new way to represent a vector on paper, okay, with just numbers. Okay, so I want to start by using that notation here. Okay, this is called algebraic notation, and it's where you just put a bracket. You write your horizontal component, your vertical component, and then you end with another bracket. All right, so for two vectors to be the same, okay, what that means is they have to have the same horizontal components and the same vertical components. When you write a vector in this notation, it tells you the horizontal, it tells you the vertical component, but what doesn't this notation tell you? Yeah, it doesn't tell me where to put the vector. So let's say you gave me the vector 2, 3. I put it anywhere I want, as long as it's always 2 to the right and 3 up to go from start to finish. So here's the start, 2 to the right, 3 up. That vector is exactly the same as that vector. Even though these vectors have different initial points and different terminal points, that doesn't mean they're not equal. They are. Okay? For two vectors to be equal, they just have to have the same initial and same horizontal and vertical components. Right? So basically, if you drag them on top of each other, they would look like they're the same. Okay? Any questions on that idea? So that's what it means for two vectors to be equal. And there's a picture. All right, so that way you can write a vector is fine, but it's not the most common way. Okay? The last way that we're going to look at for writing a vector is called unit vector notation. Okay, I brought up that term yesterday, unit vector. Does anybody remember what that means? If you have a vector that's a unit vector? What is? Something to do with 1. Yep.
It's equal to 1 unit. Well,
What's equal to 1 unit? What about the vector?
the vector from the initial point to the end point.
So what is that 1 unit measuring? Not momentum. It is a word that begins with M, though. It's magnitude. Okay? A unit vector is a vector that is 1 unit long. Okay? So I'm going to show you two special unit vectors. Okay, they have names. And the first one is I. I is a special unit vector. And it's a unit vector that points to the right. So if you want to see kind of a picture of it, there's a picture of it at the top of the next page. That's the unit vector I. It's 1 unit long, and it points to the right. Okay. Another special unit vector we have is J. And again, that would be bold. So J is a unit vector that's 1 unit long, but it points up. And what we're going to do is kind of look at these two vectors as building blocks. Okay? We're going to use combinations of I's and J's, and we're going to stack them together to build other vectors. And once we do that, that's going to lead into the final way that we can write a vector. And it's the way that's used most often. Okay? And it's, again, it's called unit vector notation. Now, I is movement horizontally. J is movement vertically. Now, if we were doing this in 3D, we would need one more. Okay? You need as many unit vectors as you have dimensions. We have 2D. We're doing 2 vectors. Does anyone think they know what the name would be for the third one? Yeah? Yeah, it would be K. K would be a unit vector that allows us to move in and out of the board, okay, 3D. Or you call that the z-axis. All right? But for today, we're just going to stick with 2D. All right, so what I want to do is build the vector 3, 4 using i's and j's. So I'm going to make what's on the right a little bigger. Okay, and I'm going to draw it as a position vector, which means I'm going to start at the origin. And from this point, to get to the terminal point, am I going to go left or right?
Right.
Right. How many? 3. So I'm going to go 3 to the right. And to get from here to the terminal point, I'm going to go how many in what direction? Up 4. All right, so there's the vector 3, 4. Now, I want to see if I can build that using these i's and j's, okay, by stacking them together. Let's make them in different colors so you can see them. Right, let's start with the i's. How many i's would I need to start moving from the initial point to the terminal point?
3.
Yeah, I would need 3 of them. So I'm going to make 3 copies of it. And I've got 1, 2, 3 i's. Okay, so I'm going to write that down. 3 of the i's. Plus, I'm going to add something on to the end of that. Okay, how many j's would I need?
4.
Yeah, I'm going to take and make 4 copies of that. And I'm going to stack those together, okay, right on the end of where I just finished. So there's 1, 2, 3, 4. So I just did 4 of the j's. That is how you can write this vector. 3 of the i's plus 4 of the j's. Okay, and this notation, that's called unit vector notation. 3i plus 4j. And that's it. That's all there is to unit vector notation. So basically, just think of it as stacking i's and j's together.
So basically, we can just take the vector points that it gives us right there and just put i's and j's with it.
And take away the comma in the brackets.
Okay.
Yep. Now, the problem is I moves to the right and j moves up. Does that mean I'm always going to have to do vectors that are in the first quadrant?
No.
How would I do other quadrants?
Negative.
Yeah. If you make I negative, instead of pointing to the right, it could point left. And if you make j negative, instead of pointing up, it would point down. So by combining any combination you want of positive and negative i's and j's, you could get to any point anywhere on this plane. Okay? You can get anywhere you want. You might have to go, 1, 2, 3, 4 and a half I, but you can do that. Okay, that's fine. All right. So any questions on the idea of building a vector out of i's and j's? Okay, from now on, I'm not going to show building it like that. We'll just directly translate basically the way Travis said from one to the other. All right, so we're going to look at some formulas for doing some things we've already done. We did a lot of things visually yesterday. Okay, today I want to kind of step back from doing it by drawing a picture, and I just want to do things with arithmetic. Okay, much, much faster than having to sketch the whole thing out. Okay, so the formulas that I'm going to show you are going to use 2 vectors, Okay, V and W stand for vectors. And alpha is going to be a scalar. Remember, a scalar is just a number. 2 is the scalar for V. Okay, it's the number that you're multiplying a vector by. The reason I use alpha for the symbol is because that's what your book does. Okay, but alpha just represents a number. Okay, so the first formula I'm going to look at is how we add two vectors together. If I was going to do this the way we learned yesterday, say I had that vector and that vector. If I want to add these up, okay, I have to position them so they line up like that, and then I have to draw that in. Not too hard, but again, a little time consuming to have to sketch it every time. So the formula, if you have the numbers that represent the vector, you don't have to draw it. You just take the x components, add them together, take the y components, and add those together. And that's how you can add two vectors without sketching it. x1, y1, x2, and y2, those will all be numbers in a problem. Okay? So you'll be able to add them. How about subtraction? It's almost the same thing, but what do you think would change in the formula?
It would be x2 minus x1 and y2 minus y1?
It could be if this order was switched. But you said x2 minus
Yeah,
x1.
I get what you're saying.
So since it's v minus w, you're going to take the x1s and subtract the x2. Right? But it could be the other way around. It's not this time. And this gives us a much, much faster way to do subtraction. Okay, doing it visually, you'd have to take w, you'd have to flip it around, and then you'd have to add it onto the end of v, and then you'd have to connect the diagonal. This is a lot easier. But if you want a picture, you got to go back to the way we did it yesterday.
So what's the point behind all these formulas?
So it gives you a way to add and subtract vectors without drawing them.
All right,
That's it.
all right. I wasn't understanding,
So we're gonna do a problem like this in a second.
all right.
I'm going to give you two vectors, and I'm going to say add them together. But I don't want you to draw anything. I just want you to write the answer with numbers. And then I'm going to say subtract them. And you're not going to have to sketch. Okay, so we're moving away from sketching for basic stuff. Okay? How about this? When you put a number in front of a vector, what does that do to it? It's multiplied, and what's the effect on it if you do that? Changes its magnitude, so it could make the vector longer, could make it shorter,
Reverse it.
and it could reverse the direction if it's a negative. Yep. So basically, to scale a vector, what we used to do, like let's say I wanted you to find 2v. Okay, pretend that's v. You'd have to take that, make a copy of it, stack it together, draw your arrow, and that's 2v. Well, now, all I'm doing is saying, take the x component, multiply it by the scalar, take the y component, multiply it by the scalar. So if I wanted you to say, take this vector and triple it. Okay, I want to make it 3 times as long. Triple the first number, triple the second number. Done. Okay, you don't have to draw 3 of them stacked together. You just triple each component. So in that case, it would be 6, 9. In fact, I think we're going to do that in a second. Okay, so the first 3 we've done before. We did them visually. Now we're doing them with just numbers. Okay, we're not going to draw it. This we haven't done yet. Okay, I showed you what the symbol means, but we haven't done it. What does that symbol mean when you put double bars around a vector? What do we say? Absolute value? It's not absolute value. It has something in common with that. What does absolute value measure? It measures the distance. Okay? This is distance, right? This is the length of the vector. So if I say I drew a vector from here to here. How could I find the length of what I just drew? I can't count, right? If I went like this, I could just count. 1, 2, 3, 4, because it's straight. But this is kind of at an angle, so I can't count. Thoughts how I could get the length of that? Yeah? Do what?
Hypotenuse.
Okay, if you think of that as a hypotenuse, keep going.
Then you can basically draw a line underneath to count how many squares you with it and up.
All right, so I went 1, 2, 3, 4, 5. Yep.
And then if you go up,
1, 2, 3. Okay.
you can find the hypotenuse of that.
How would you do that? Pythagorean theorem. Exactly. So if this is your x component, pretend it's not 5. In general, it would be x, and that's your y component. The Pythagorean theorem says we take each one of these and do what? Square them. You square each one of them, and then what do you do with them? You add them up. And then lastly, take the square root, right? Because that's equal to the hypotenuse squared. So you take the square root. So there's your formula to find the magnitude. Square root of x1 squared plus y1 squared. It's just the Pythagorean theorem. So we'll go through an example of one of each type, and we'll practice writing our answers both ways. We'll try writing our answers with the IJ notation, and then with the angle brackets. Okay, you should be familiar with both. And they're both. If you can do one, you can really do the other. Okay, so we'll start with V plus W.
Can we go back to the last equation real quick? So I can- Thank you.
Yep. Does anybody else need that? All right, so I want to add these up. So basically, look at the numbers in front of I, add those up. Look at the numbers in front of J, and add those up. So let's start with I. If I add up my horizontal components, what would I get for V plus W? So 5, and let's do it with the I notation first.
Okay.
So you get 5I. And what about if you add the J components? How much?
-1.
Yeah, you get -1. 3 plus -4. And you can put -1J, or what could you just write? Just -J. Yeah. So if you add those vectors together, that's what you get. 5I minus J. How about written this way? Yeah. Same thing, just a different way to write it.
Is it gonna stay this easy?
Today?
Oh.
He's like, is it going to stay this easy for today?
In general.
No.
Today?
No.
He goes.
Okay, V minus W. All we got to do is take the V's and subtract the W's. Okay, so what would you get for the horizontal, or the I component, if you do V minus W? Negative I. You can put -1I, but you don't need to. And how about the j component?
7J.
Yes, be careful when you do this one because it's 3 minus minus 4. Okay, okay, so negative I plus 7j or negative 1, 7. If you write it with the angle brackets, you do have to put the negative 1. You got to put something there. But you don't have to put the negative 1 in front of the I. Okay, questions on adding or subtracting? Okay. This one we actually already did. We didn't write it yet, but it says to take vector v and triple it. Right? So if you take the I component, it's 2I. What do you get if you triple that? 6I. And the j component is 3. If you triple that, you get
9J.
9j. That's it. That's the answer. Or you can write it that way. Any questions on that? Okay, and last one, find the magnitude. Okay, the magnitude has a square root in it, so that's generally the first thing that I like to write down. Okay, so we don't forget that. And somebody tell me what I'm going to fill in for my two numbers. What squared plus what squared?
X squared plus Y squared.
Yep, and what's x in this case? 2. And y was
3.
3. Okay, so when I do this, I get square root of 13. What's different about the answer in D? D is a completely different kind of answer than A, B, and C. Yeah?
It's not a coordinate.
Kira, it's not a vector. Okay? These are all vectors. These are representations of arrows. This is not a vector. This is how long is something. It's square root of 13 units long. Okay? So there's no way to write this with i's and j's because it's not. It's not a vector.
Mr. Hager, can you unlock your little cabinet, please?
Okay.
Keep it like that.
All right. So yesterday we mentioned the idea of a unit vector. Okay, just reminder, you already have this in your notes, but a unit vector is equal to 1 unit in length. Okay? But sometimes what they might give us is they might give us a vector that's too long, and we have to shorten it down to make it a unit vector. Or the opposite. They might give you something that's too short, and you might have to make it longer, okay, to make it a unit vector. Okay, so that's what I want to figure out how to do. If they give me a vector, I don't want to mess with the length. I don't want to mess with the direction. All I want to do is make it so that it's 1 unit long. Okay? All right, so we're going to try to find a unit vector given a regular vector that's not 1 unit long. So let's say you had a vector that was 5 units long. If a vector is 5 units long, is that a unit vector?
No.
No, it's too long. In fact, it's 5 times too long. So if you had something that was 5 units long, what would you have to scale it by to make it 1 unit long? Well, if it's 5 units long and you scaled it by 5, that would make it 25. That'd make it bigger.
Then 1 or negative 5?
No, negative 5 would still make it bigger, but that would also flip the direction of it.
1/5.
1/5. Okay?
I can quit school, that's it.
So yeah, if you had something that was 5 and you scaled it by 1/5, it would be 1. What if you had something that was 8 units long? What would you have to scale it by? 1/8. Or if it was, now you got it. If it was 10 units long, it would be 1/10. Does anybody see the pattern? It's always 1 over the length. Or you can think of basically just divide by its length. Okay? So if you had a vector that's 5 units long, divide it by 5. Or multiply by 1/5, same thing. If you had a vector 8 units long, divide it by 8. Or multiply by 1/8. So if you have a vector and you want to turn it into a unit vector, divide it by its length. And that'll turn it into a unit vector. Which is the same as what Travis said. Multiply by 1 over the length. Okay, and this is how I'll probably do it. Take your vector and multiply by 1 divided by the length. So you've got to find the length first. Maybe you already have a unit vector and you don't have to do anything. If you don't, then you do. All right, so I've got the vector 3, -4. And I want to turn that into a unit vector. I don't want to mess with the direction of it. So all I can do is scale it. I can make it longer or shorter, but I'm not changing the direction. All right, so the first thing is let's find the length of v and see what we're working with, and then we'll figure out if we need to adjust it to make it 1 unit long. Okay, how do I find the length of v? What's the calculation I'm going to do? Yeah, and can you just fill in my specific values? 3 squared and -4 squared. Okay, what's 3 squared? -4 squared. And if you add 9 and 16? So how long is this vector? 5. So is it a unit vector? No. But now we know what to scale it by because it's 5 units long. I'm going to scale it by what? 1/5. Okay, it's too big. It's 5 units long. You've got to make it shorter. So scale it by 1/5. Now actually do that out. Okay, what's 1/5 times 3? 3/5. And if you scale the x component, you need to scale the other one, the y component as well. -4/5. How'd we get a fifth? Because the vector is 5 units long. So if something's 5 units long and you want to make it 1, scale by 1/5. Okay, so now here's a vector that points exactly the same direction, except now it's 1 unit long instead of 5.
Is that the hard part, or is it harder? This is the hard
That's no, that's not the hard part. That's just dividing each number by 5.
I know, why?
Well, I figure if I smile, maybe it'll give you hope that you can do it.
No, your smiling makes us like enjoy our pain.
Oh. All right, so now we're gonna take a look at the first application. What we're gonna do is a velocity vector. Okay, velocity vector is it's pretty straightforward. Basically, if an object is moving and you want to describe it, you need to tell me 2 things about it. How fast is it moving? What direction is it moving? And that's what this does. It describes the speed and the direction of an object. Okay, and what I'm going to do so I can save some time for the last example is I'm going to give you the formula for a velocity vector. Okay, they have to give you 2 things in order for you to write a velocity vector. You've got to know how fast the object is going, and you have to know the angle that it's traveling at. right? So as long as they give you this and that, you can use the following formula. Okay, so your formula is magnitude of your vector. That's your speed. So you just have to fill that number in. And then this is the angle that you're throwing it at. That's alpha. Okay, so just two things you need to fill in. And then we'll use our calculator to do it out. This is your horizontal component. It's the cosine of the angle. And that is your vertical component. It's the sine of the angle. Okay, and again, you do need to use your calculator and do those two out. So you'll be given an angle, usually in degrees. Just take the cosine of it, put that number in the first box. Take the sine of the angle, put that number in the second box. Okay, and we're going to go through an example of this right now. But does everybody have that formula? Again, this is called a velocity vector. Okay, and I already, if you just labeled the way I did up above, you don't really need to write what's below. It's the same thing. Magnitude of the vector, that's your speed, your velocity. Alpha is your angle. All right, so in our example, we're going to throw an object at 50 miles an hour. And we're going to throw it at an angle of 30 degrees. So before I even start, what does that mean? If you throw an object at 30 degrees, how is it traveling away from me? In what directions? Yeah, it's going to go up, right? Because I'm not throwing it straight. I'm throwing it at an angle. So it's going to go up, and it's going to go away from me. So yeah, it would be kind of like an arc. Okay, but the important thing is you understand that it's traveling in two directions, up and forward. Okay? It's not like I just do something straight up and it's only traveling in one direction. Okay, like up and back down. Okay. All right, so what's the speed that I'm throwing the object at? 50 miles an hour. So fill in your speed. And then cosine of, what's the angle that I'm throwing it at? 30. Okay, put an I next to it. That's your horizontal component. Plus sine of 30. And put a J next to it. Okay, question on where the 50 came from? Oh, the 50. Does everybody have what's on the left? Can make what's on the right bigger? 50. Okay, so all we did was fill in 30 for the angles, and then filled in 50 for the velocity. Now I'm going to find what is the cosine of 30 and what's the sine of 30. Okay, so we're going to do those two things out. Cosine of 30 is 0.866. I, okay, that's the horizontal. And the sine of 30, that's 1/2. I just know those because 30 is an angle we use a lot. Now I still have the 50 on the outside of the parentheses, so what should I do with that 50? Yeah, multiply it to each component. So I've got 50 times 0.866, which is about 43.3. I, so that's the horizontal. And what's 50 times 1/2? 25J. that is my velocity vector. Now, the last part of the direction said explain the meaning of that number and that number. And I tried to give you a hint earlier when I asked you about the object traveling. So does anybody know what this 43.3 is? Okay, remember, this is all velocities. But the 43.3 is a special velocity for this object.
It's how far it's moving away from you, like to the right.
Not how far it's moving away, how
Fast.
fast. Okay? This is the speed in the horizontal direction. So if you were throwing this object at a wall, that's the speed it would hit the wall at. It wouldn't hit the wall at 50 miles an hour because you didn't throw it straight at the wall. You threw it up and straight. So some of the power you put into it is making the object go up, not forward. Okay? And how about the 25? Yeah, that's the speed in the vertical direction.
So did you have to take like a physics course to learn this, or you only took a trig course?
I had physics in high school, but no, I didn't take any physics in college. No, it was in high school. So now, if the way you could imagine this 25 is, imagine you were in like a blimp, okay, above a baseball field, and you saw two players on the baseball field throw the ball to each other, like in the outfield, okay, and they arced it. They didn't throw it straight, they arced it. And if you pointed a radar gun straight down at the baseball, that's the speed that you would register. It's not the speed it's traveling at the person. It's the speed that it's going up towards the blimp at. Okay, because it's going up towards the blimp as it arcs towards the other person. And if you know how fast you throw something up, you can tell how high it's going to go. And if you know how high it's going to go, you know how long it's in the air for. Okay? So then you can figure out other things, like how far did the ball go before it hit the ground. Okay? But for us, that's all we're going to figure out. There's all kinds of things you can do with that. Yeah. All right, so any question on the velocity vector? Okay, so it's really pretty straightforward. You just fill in the two numbers and do your distributive property, and that's it. You don't even have to explain the two components. Just stop at the box. But I wanted you to understand what they were. Questions on that? Okay. So, last thing we're going to look at is what's called static equilibrium. Has anyone done static equilibrium before? Maybe. I don't know exactly what you teach.
We did equilibrium plenty of times, so I'm sure.
So what does static mean? Like, it's what? Yeah. Okay, static. Static means that your object is staying still. Okay? And what about equilibrium? Things are the same, right? Things are balanced. So we're looking at objects that are staying still because things are balanced. Okay? Everything that's not moving in this room is in static equilibrium. Right? Any object sitting on any surface, it's not moving because the force of gravity pulling it down and the force of the desk pushing up are the same. That's why it's not moving. If you ever have a force that's unbalanced, then things move. Okay? So we're going to look at static equilibrium from the perspective of 2D. We're not going to do 3D. We're going to look at it in terms of 2D. So if all the forces acting on an object are zero, then you get no movement. You can still have a lot of force happening. Think of like a tug of war. Right? If two teams are pulling really, really hard, there's a ton of tension in that rope. Like if you cut it, like everybody would fall. Right? But if each team is pulling equally as hard, that rope is in static equilibrium. It's not moving because the forces pulling left and right are the same. But there can still be a ton of tension in that cable or in that rope. And that's basically what we're going to figure out. we're going to find the tension in a cable supporting a weight. Now, if you had a cable, okay, hanging from the ceiling, attached to an object, just a single cable, that one cable would be holding all the weight of the object, right? So if I had a rope and I'm hanging from it, and you weigh 200 pounds and you're hanging, that rope has 200 pounds of tension in it. But if you split it and you put two cables attached to it, then things change a little bit. Okay, each cable is sharing some of the load. But it's not necessarily like, say, 800 pounds in one cable and 400 pounds in the other. It doesn't work that way. Okay, you can have more tension in the cables than there is weight of this object. Right? Think of like a rope in a tug of war. Right? Essentially, there's no weight hanging from the rope. Right? It's just a rope between two people, but you can have a ton of tension in that rope, even though there's no weight hanging from it. It's just because people are pulling on it very hard. Okay, so basically what I want to do here is find the tension in each cable. All right, so we're going to pretend that like each of these ropes are vectors. Okay, and I'm going to call the rope on the left T1, because it's going to stand for the tension in rope 1. And the rope on the right, T2. Now, if you look at T1, what direction is cable T1 pulling in? Or directions? Think about what would happen if you cut T2. You just cut it right now. What would happen to that weight? It would swing to the left, so that means T1 must be pulling to the left. Okay? But would the weight fall to the floor if you cut T2? Would it fall? No. No, assuming T1 is strong enough cable to hold it by itself. No. So the weight would still be hanging in the air, so the cable must be pulling up, right? But it also is pulling to the left. Now, how about T2? What directions is that pulling in? It's pulling to the right and up. Think about if you cut T1. All of a sudden that weight would want to swing to the right because T2 is pulling to the right. But it wouldn't fall to the floor because T2 is also pulling up. Right? So I'm going to try to draw that in, what we just said. Okay. Temporarily, what I need, because my board is so big it's hard for me to do it, I just need like a guideline to show me where I'm going to draw something. You can probably do it on paper if you drew your diagram small enough. But basically what I'm going to do is create some triangles. Okay. T1 is pulling left, and it's also pulling up. Okay. And this is exactly the kind of diagram we did when we added vectors together. Okay. Add the red and add the blue, and you get the first rope. All right. T2, it's pulling to the right, and it's also pulling up. Okay. I don't need these green dotted lines anymore, so I can just move them out of the way. Now, I created two triangles, but what kind of triangles are they? They're right triangles. Now, I have some angles that are labeled on the outside, but I need the angles on the inside. And typically, I don't need both of them, but you could label both. What would the angle on the inside at the top be?
60.
Yeah. This whole angle is a 90. So if that's 30, what do you add to 30 to make 90 is 60. And then how about this angle at the bottom?
30.
That's a 30. We don't need both of those. But we do need one of them. Doesn't matter which one. How about the angle at the top
45.
and the angle down at the bottom?
45.
Yeah, they're all going to add to 180. 45, 45, 90. All right, now the next thing, we gave a name to the hypotenuse, T1 and T2. I need names for the red and the blue lines. The red lines run left and right. So what letter do we normally use to represent left and right axis? X. Okay. So
Okay.
let's call the arrow that's going left, we'll call it our first X. And the arrow going to the right, our second X. What do you think I could name the blue arrow that's pointing up on the left? Yeah, it's my first Y. And how about on the right? Y2. All right, so now we've named everything. Now we can work with it. All right, so first thing I'm going to do is just kind of set up the concept, and then we'll try to figure out numbers. So these cables are both pulling in two directions, horizontally and vertically. Now, if the object isn't swinging horizontally, what does that mean about the force that's pulling it to the left if it's not swinging? It's equal to what? The force that's... Exactly, the force pulling to the right. If the force left and force right were not equal, this object would be swinging. All right, that's one dimension. The other dimension is up and down. Is the object being pulled up, or is it falling to the floor right now? It's static. It's not moving. So that means the force that's pulling it up is the same as what? Same as the force pulling down. Okay? So this is getting us towards that system of equations we're going to have to solve. There's no numbers in here. This is just a concept. Force pulling left and right is the same. Up and down is the same. Now, in the diagram, what is the force that's pulling us left? What did we label it as? X1. And what's the force pulling right? Okay. What's the force that's pulling up? Y1 and Y2 are working together. And what's the force pulling down? 1,200. All right. So now these are the equations we need to work with. The only thing we have to figure out is how do we write X1 in terms of the tension in the cable, because that's what we really want. We want the tension, and we got to use the angle somehow. Okay, they gave us these angles, we haven't really used them yet. So let's start with X1. Okay. We've got a right triangle, okay, and we reviewed this earlier. What's the name of the side that's right next to the 30-degree angle? We've called it X1. It's adjacent. What's the name of the other side that's what's the name of T1? It's the hypotenuse. So if you have adjacent and hypotenuse, what trig function do you always use? No, that's opposite and adjacent. Cosine. Okay. So I'm going to set up a formula for X1. Cosine of 30 equals, what side is adjacent? What did we label it as? X1 over, what's the hypotenuse? T1. Now my goal is, I'm trying to find a formula for X1. Okay, I need something I can plug in for that. How do I get X1 by itself? Oh, so T1 cosine 30. That is X1. Okay, and eventually that'll go right there. Okay, let's do X2. Eventually you're going to start to see a pattern with the answer. Maybe after this one you'll start to see it, and then you don't need to go through every step every time. Okay, let's look at X2. I want to use this angle, this, and that. Okay, what's the name of the side we called x2? Adjacent. What's the side that's t2? Hypotenuse. So what trig function? Cosine. So I've got cosine. This time my angle's not 30. My angle is 45 degrees. I'm in that other triangle. Okay, the side adjacent, x2. The hypotenuse, t2. And now how do I get a formula for x2? Multiply by t2. t2 cosine 45. So there's our formula for x2.
Excuse me, Mr. Hager.
Okay, so here's t2. Now, if you notice the pattern, anytime you're working with forces that are horizontal, just use cosine. It's the hypotenuse, cosine, angle. Every time. Hypotenuse, cosine, angle. Now, let's do y1. And then I think you'll see the pattern for y2, hopefully. And hopefully you see the pattern in general, so you don't have to go through all these steps if you have to do it. All right, y1. We're using this angle, this side, this side. So focus on the three things in green. What's the name of side y1? Opposite. What about t1? Hypotenuse. What trig function has opposite and hypotenuse? Sine. So it's going to be sine of 30 equals opposite over hypotenuse, y1 over t1. These are all very similar in how they're set up. So what would y1 equal? Yep. T1 sine 30. So anytime you're working with vertical forces, it's always hypotenuse, sine, angle. So let's see if we can get y2 without doing all that work. Hypotenuse, sine, angle. Okay. What's my hypotenuse in the triangle with y2? T2. It's hypotenuse, sine. What's my angle? 45. Okay, that's always the setup. Okay, so now we've got y1, we've got y2, we've got x1, and we've got x2. Any questions on that? It's basically 4 right triangle problems. Okay, so now as far as the kind of the physics part, that was done at this step. That's that concept. The trig part is these 4 boxes. Okay, so now the trig in this problem is done. Now we fill everything in to those 4 spots, and then it's an algebra problem. That's a system of equations. Okay, so we'll fill it in, and we'll see if we have time to finish it. So put x1 equals x2. T1 cosine 30. X1 equals T2 cosine 45. Now don't get confused by T1 and T2. That's just like having an X and a Y. They're just 2 different letters. That's all. Now the other equation, y1 plus y2 equals 1200. So y1 plus y2, that's the force pulling up plus the other force pulling up equals the force pulling down. You don't even have to think about forces anymore. You can forget physics and just pretend it's just numbers now. You don't have to think about cables and tension and triangles. Okay, so now we solve these 2. All right, let's look at the top one. which I'm going to call equation 1. Pick a letter here that we want to get by itself, T1 or T2? T1. So, how would you move cosine 30 to the other side?
Oh, inverse.
Think of it just like this. A letter times a number equals a different letter times a different number. So how do you get the letter by itself?
Why don't you divide cosine 30?
Yeah.
Yeah.
Just like here, you just divide by the number that's next to your letter. Okay. Same thing here. Divide by the number that's next to your letter. So we have T2 cosine 45. And what are we going to divide by? Cosine of 30. So we just picked one of the equations, and we got one of the letters by itself. Now, what do you do once you get something by itself? You all got it when we did it earlier. I know you know how to do it. So what do you do with this?
You plug it into what? Yeah.
Plug it in where?
To the original equation.
Yeah, plug it back in for one of your letters. Okay? Now, we've got all these sines and cosines. You can do all those out. Change all of them to decimals if you don't like them. Okay, we're going to have to anyway. Right? But I'm going to fill in for T1 what we just said it was. It's T2 cosine 45 over cosine 30. That's T1 times sine 30, which you could just put right next to it, plus, and now just copy the rest of the problem. T2 sine 45. I know it is messy, but now we're going to type everything in on the calculator. Okay, I'm going to type all this stuff in next to T2.
Go ahead. Let's try it. Error.
First, what mode is my calculator in? Put it in degrees. You got cosine 45 times sine 30. And what do I divide by? Divide by cosine 30. So you get 0.408. So all of this is gone. Just 0.408T2. Plus, sine of 45 is 0.707. Just trust me.
You're like a human calculator.
I just have it memorized. Now, what can you do with these two things? Yeah. Take, okay, guys, I need you to be quiet, okay? Take 0.408, 0.707, and hit plus, and it adds them up. 1.115. And now it would be our last step, and we'd have the tension in cable 2. Yeah. Divide by 1.115 on each side. So the tension in cable 2 is 1,076 pounds, roughly. What did I say? 1,076 pounds. Now, to get the tension in cable 1, you got to do it all over. No.
That's only for cable 2? Yeah. No. Are there any of these in the homework?
No, we have right here. All you have to do to get the tension in cable 2 is fill in for T1. Actually, right here is even easier. You just figured out T2 is 1,076.
Oh, just plug it in. Okay.
Just type it in right there and multiply by cosine, divide by that, and you get T1. Okay, so there was a lot of steps in that problem. So on the homework, there's one of those, but it's exactly the same thing. So even if you don't understand how to do it, just change the angles and copy the same work. Okay? Okay, so that's the homework for tonight.